Okay, for question 2, what we are actually given is a curve C whereby the equation is given as a parametric form. Okay, x equals to et minus t square minus 1, y equals to et plus t minus 1. Now for part 1, we are actually given a point P on C whereby the parameter for this particular point is actually t equals to 0. And you are actually supposed to find the equation of the tangent at this particular point P. Now, to actually find the equation of tangent, the very first thing that we actually need to do is to actually find dy dx for the curve C. Now, since the equation of the curve is given to us as parametric equations, what we will actually have to do now will be actually to go and find dx dt, dy dt, and then dy dx can be found by using dy dt divided by dx dt. Now, after you actually get the expression for dy dx, please take note that you are supposed to sub in the value of t equals to 0 into the dy dx so that you can get the value of the gradient, okay, at the point P. Now, take note, dy dx itself, if you don't actually sub anything in, it's just an expression for you to actually find the gradient, okay, for the curve C at various points. So after you actually determine the value of the gradient, then we will be either using y minus y1 over x minus x1 equals to m, where m is the gradient, or y equals mx plus c to actually determine the equation of the tangent at P. So with all this said, we are ready to actually solve question 2. So the equation is x equals to et minus t square minus 1, y equals to et plus t minus 1. So dx dt is equals to et minus 2t. dy dt is et plus 1. So dy dx is actually equals to et plus 1 over et minus 2t. This is only the expression for dy dx. So in order to get the gradient, so for the gradient at P, okay, we know that t equals to 0. We will sub in, okay, we will sub in t equals to 0. And this will give us the value 2. Now, once we actually get the gradient, we also need to know the coordinates of the point P itself. So for t equals to 0, we will actually put this value into the parametric equations. So and y is actually equals to okay, both x and y is 0 means that we are actually looking at the origin. So the equation of the tangent, okay, at point P. Okay, for my preference, I'm going to use y minus y1 over x minus x1 equals to the value of gradient, which is 2, and you will actually get the equation of tangent at point P to be y equals to 2x. Now we come to part 2 of question 2. Now, we are given the fact that the tangent at P will meet the curve C again at point Q, so we are supposed to find the value of t at this particular point Q. Now, to actually solve these questions, we actually found from part 1 that the equation of the tangent is y equals to 2x. So basically, to actually find this point Q, which is the intersection between y equals to 2x and the curve C, we are supposed to find the intersecting point between this curve, which is in parametric form, and the curve C, which is in this equation here, the equation of tangent, which is in Cartesian form, okay, and the curve C, which is in parametric form. So how to actually find the intersecting point between one Cartesian equation and another parametric equation is that we will actually sub this x into this equation and this y into this equation. And from there, we will be able to get the following. Okay, so tangent, equation of tangent y equals to 2x. The equation of the curve C is like this. So what we will do? We will do this substitution. And from there, it means that with one equation in terms of t, we can actually solve for the values of t. But please take note one thing is that you are actually now having an equation that contains exponential and algebraic form. This will mean that we will be using GC to actually solve for this value of t. So since we are going to use GC, a more convenient way is to actually shift all the terms to one side. Okay, why we actually shift all the terms to one side is that if now I key in this particular expression into the GC, what I just need to do is to actually find the x-intercept. So using the GC, okay, I already key in the expression already, graph it, and do take note that you see that there's two x-intercept, one at x equals to 0, which is actually t equals to 0, which you should expect because the tangent will actually intersect the curve C at point P, whereby t is equal to 0. So the x-intercept for point Q is actually this x-intercept here. So to find it, calculate 0, go for the left bound, okay, go for the right bound, and to get a more accurate value, choose for when you actually prompt to guess, shift the cursor as close to the point as possible. You will get the value to be 3.21. Hence, we will actually, to be more complete for our solution, we will say there's two solutions to it, t equals to 0, which is point P, and t equals to 3.21, which is for point Q. Okay, for part 3 of this question 2, first thing first is we have to show that e to t minus 2t is bigger than 0 for all real values of t, and then later deduce whether c is strictly increasing or strictly decreasing. Now, take note that when you actually see this term, how to actually show c is strictly increasing or strictly decreasing is that we will actually have to look at the behavior of dy dx. And for this particular question, we already found the expression for dy dx from part 1. Now, so if c is strictly increasing, you should have dy dx more than 0 for all the points. And if it's strictly decreasing, you should have dy dx less than 0 for all the points. Okay, but first, how to actually we show that et minus 2t is more than 0 for all real values of t? Now, take note that this question never actually implement any restriction on our solving techniques, so the most convenient way will be actually to use GC to actually sketch the graph y equals to ex minus 2x. So go to the GC again, okay, I already put in the equation ex minus 2x, and when you actually graph it, you can see that the whole graph actually lies above the x-axis. So how to actually present your solution? Well, do a simple sketch of the graph. Do use ruler during exams, please, okay. So this is y equals to, okay, if you actually want to actually make it more related to the question, you can call the axis, okay, the horizontal axis to be t in terms of x, so that you can call your equation to be y equals to et minus 2t. So since the graph of y equals to et minus 2t lies entirely above the x-axis, sorry, the t-axis, since I actually use t to represent the horizontal axis. Therefore, et minus 2t is bigger than 0 for all values of t. Then the question actually then asks us to actually deduce whether c is really increasing or really decreasing. So what we will actually need to do is that we actually go and need to find out what is our dy dx from part 1, which is here, et plus 1 over et minus 2t. Okay, et plus 1 over et minus 2t. So first thing, et plus 1 is definitely positive because we know that the graph of the et is actually more than 0. So plus 1 already is actually positive. And et minus 2t we have just shown that it's actually more than 0. Therefore, okay, for all values of t to be more complete in our solution, okay, therefore dy dx is bigger than 0 for all values of t implies C will be strictly increasing. Okay, for the last part of the question, we are just going to sketch C, so we are going to be using our GC to help us to sketch. So we'll go to our GC. First thing first is please change your mode to parametric. Okay, key in the equation. But before you even start to press the button for graph, please go to Windows and change the T minimum. Now, do take note that by default, your GC will always have T minimum to be equal to 0. However, if you actually read the questions carefully, there's no restriction on the value of T. Hence, please give a suitable value for T minimum, okay, a suitable negative value, so that you can actually get the whole graph. Okay, and do take note, we have already shown that C is actually strictly increasing, and this graph actually exhibits this behavior. Okay, so to actually sketch, just okay. Let me check the graph again. Okay. Okay. And we are done.